Okay, in this third video, we're going to be continuing to work with we're going to continue working in dynamics. We're going to continue working with Newton's second law. So we're going to continue working with F equals ma, and now we're going to be looking at applications of F equals ma with regard to tension. Okay, so tension is defined as a force along the length of a medium, so especially a flexible medium. So we can think of a rope or a cable or a chain here or something, and the tension is just the force that chain or rope is exerting on whatever mass we're looking at. So I have three different examples that we're going to look at in this video of sort of increasing difficulty as we go along. And this first one is just really to demonstrate like sort of what tension is, and the next two are more like ones you might see on an assignment or on a midterm or something, right? Okay, so let's take a look at these three examples. Our first example here is simply a 5 kilogram mass that's hung vertically from a rope, and we want to know what the tension in the rope is. Okay, so let me just draw a picture here. We're going to have a mass. It's going to have some force of gravity pulling down on it, so Fg, and we know this is just going to be equal to mass times our gravitational acceleration, so mg. And there's going to be some rope. Let's say this is our rope here, and in the rope we're going to have some tension that's sort of keeping this thing stable, right? So if we were to make a free body diagram out of this, what we would end up with is our mass here. We're going to have the force of tension pulling upward, and maybe I won't do this with vector symbols, so I don't have to do that on the bottom, and then mg down over here. So what do we want to do? Well, we want to apply Newton's second law to this. So this means that Newton's second law tells us that F net in the y direction, we don't really have to include that y here since there's only one direction that we're looking at. So F net is equal to ma, the acceleration in that one direction, and that is equal to t minus mg, right? So t in the positive y direction, if this is our positive y direction, then we have t minus mg. But this mass is not accelerating, right? It's just hanging on this rope, so this a is 0, which means that this is equal to 0, right? Because if a is 0, then that term goes to 0. And so what we have is t is equal to mg, right? We can just shift the mg to the other side, and quite quickly we can solve for what t is, right? So we have t is equal to, well, what's m? We're given m up here in the problem. It's 5 kilograms, so that's going to be 5 times 9.8, and this means that we have a tension of 49 newtons in the cable or rope or whatever, right? Okay, so that kind of just gives us a very simple idea of what tension is. Let's move on to our second example for today. This is an example from the text, 4.6. It's a little more complicated, and let's take a look at it now. So what do we have here? We're looking at the tension in a tightrope. So we want to calculate the tension in a wire that's supporting a 70 kilogram tightrope walker in the following configuration. So I'm drawing the configuration down below here. Assume the tightrope walker is in the middle of the tightrope, right? So let's take a look. Let's take a look at the diagram here. This solid line here, this is our tightrope. So the tightrope is kind of like bending downward a little bit as this person's walking across it. There at the midpoint, we have their mass at 70 kilograms, and we have an angle theta here. We can see these angles theta here and here, which I've labeled as each being 5 degrees here. So both of those angles are the same. They're both 5 degrees. And what we want to find is what the magnitude of TL and TR are. So TL is the tension in the left-hand side of the wire, and TR is the tension in the right-hand side of the wire. Maybe they'll end up being the same, maybe they won't, but we're going to calculate them now, okay? Okay, so this is a little more complicated. We can't just right away jump into it. So the first thing that we probably want to do is we want to take a look at a free body diagram. So I'm gonna draw our first free body diagram here. So one tempting way to draw this might be to just reduce down our tightrope walker to a dot, and then we're going to have mg in this direction, right? Downward, the force of gravity. Then we're going to have the tension of the cable on the right here, so TR in this direction, and TL in this direction, and we were going to end up having some angle theta in here, right? So this is good, but really we want to be working in orthogonal coordinates, right? So we need to choose a coordinate system that's going to be handy for us to work with, that we can sort of break up these vectors into those directions and then work with them, right? And the easiest way to do that, at least the way that I've chosen to do that, is by trying to get to this free body diagram that I'm going to draw here. Okay, I'm going to call this free body diagram 2. So if we were to break up the left and the right tension into their vertical and horizontal components, we could draw something like this, right? So imagine we have our mass in the center. We still have the force of gravity going this way, but let's say we extracted out the portion of the tension pulling to the right and to the left, sort of in the x direction. Like imagine we're imposing a set of xy coordinates like this. So this is x, this is y. So if we extract out the portion of TL and TR pointing in the x direction, we would end up with a TR x component pointing in that direction, and a TL x component pointing in that direction, right? So we're pulling out the part of this and this vector which are pointing in the x directions, and so they would point in opposite directions, obviously. And then vertically, we could pull out the y components of TL and TR, and we would end up with TRY and TLY, right? And so those would be the vertical components of the tensions in both of these cables, or in both sides of the cable, right? And so this is really what we want to get to, because when we're in this setup, we have everything pointing in either the x or y direction. We can break it up into the two directions and solve the problem, okay? So that's what we're going to do. We're going to start off by breaking our tension left and tension right, so TL and TR, into their vertical and horizontal components, okay? So I'm going to write this down. Okay, so this is what we want to do. We want to break up our tensions into their vertical and horizontal components. Well, let's take a look at one of them, right? So let's take a look at how much space do I have here? Okay, so let's take a look at TL first of all, let's say. So we have TL. What does TL look like? Well, TL is kind of a vector pointing like this, right? We know that we have some angle theta in here, and this is TL. But we want to break this up into TLY in that direction and TLX in that direction. And if we think about the sort of tools we used to break up vectors before, we're going to use the same idea again here. So always we want to have in the back of our mind this SOHCAHTOA or whatever mnemonic you use to remember sort of how sine and cosine and tan work with different angles, right? And so if we do that, we can pretty much right away see that we want TLY to link up with our opposite side, right? And so what does this tell us? Well, if we think about it, we're going to find that TLY is just equal to TL sine theta, right? And TLX is just going to be TL cos theta, right? Because we want the adjacent angle, which goes with cos, to be connected to our x direction, and the opposite angle, which connects up with sine, to go with our y direction, right? Opposite from the angle theta, right? And if we did the same sort of argument, we could do the same thing for tr. We would just end up with our tr like this, some angle theta in here, and what we would want is tr y here and trx here, and again the same thing. We'd get the same result basically. So we would end up with tr y equal to tr sine theta, and trx equal to tr cos theta. Okay, and so that's how we would break these things up, right? So that's great. We now have expressions for sort of all of the vectors in our free body diagram, and that's what we should be aiming for. Okay, so now what? Well, now what we're going to do is we're going to take a look at the two different directions, right? We're going to take a look at first what's going on horizontally. So let's take a look at first, well, is there any acceleration in the horizontal direction? Well, no. The piece of the cable over which the tightrope walker is walking isn't accelerating. It's just stationary there. So there is no acceleration in the x direction. So ax is equal to 0. And so let's now take a look at Newton's second law with regard to this horizontal direction, right? So let's take a look. Or maybe I shouldn't do that. Let's do this. N2 tells us that F net in the x direction is going to be equal to ma in the x direction. Okay? And so since we know that there is no acceleration in the x direction, that means that this is equal to 0. But F net is also equal to, and again, let's assume we have a coordinate system like this, where this is our x and this is our y. So in the positive direction, we have trx, and in the negative direction, so we then have to subtract off tlx, right? So we have trx is equal to minus tlx, trx minus tlx is equal to 0, which tells us that trx is equal to tlx. And then we can substitute in the values that we found for trx and tlx up here. And this is going to give us, well, trx is equal to tr cos theta, and that's equal to tl cos theta, right? And so because of that, we can isolate one of these. So let's say we divide through by cos theta. This tells us that tr is equal to tl. And in this case, this wouldn't always be the case, but because of the symmetry of the problem, because we have the tightrope walker right at the midpoint, in this case it ends up that tr and tl are equal. So the tension in the cable on the left is the same as the tension in the cable on the right. So let's just relabel this. Let's just call this t, and that'll be equal to both the tension in the right and the tension in the left. Okay? So that's good. We've found out that the tension is the same in the right and the left, but we don't yet know what the value of that tension is. How are we going to find that? Well, let's take a look at the vertical direction. Okay, so this was horizontal. That was the horizontal direction. Let's now look at vertical. Okay, so vertically, what's going on? Well, let's go to Newton's. Well, first let's see that there is no acceleration in the y direction either, right? Let's notice that there is no acceleration in the y direction. This tightrope walker isn't plummeting to the ground or shooting up into the sky. There is no acceleration in that direction. So then Newton's second law tells us that F net in the y direction is equal to mass times the acceleration in the y direction. And as we just said, this is 0, so it's going to be equal to 0. But what is F net in the y direction? Well, F net in the y direction is the total of all the forces acting in that direction. And so in the positive direction, we have try and tly. And then in the negative direction, we have mg, right? And so because we've seen that these three terms all total up to 0, we can isolate two of them. So let's rewrite this like this: try plus tly equals mg. Okay, and now we also have expressions for tly and try in terms of TL and TR, which we now know are just T, right? So we can rewrite this as I'll do it in 2 steps, so we don't confuse anyone. So this is going to be TL sine theta plus TR sine theta equals mg, but we just said that TL and TR are the same thing, so this is just going to be 2T sine theta equals mg, right? So we got 1 T sine theta from each of these because TL and TR are each equal to T. And then we just want to solve for what T is, right? And we can do that simply enough. Simply isolate the T, and this is just going to be mg over 2 sine theta. And at this point we know all these variables. We know what m is, we know what g is, we know what theta is. We just need to solve for t. So if we were to do that, we would end up substituting in, well, here I can write it out, 70 times 9.8 over 2 sine 5 degrees, right? And if you put that into your calculator, you're going to find that t is equal to 3,935 newtons. And that, well, we also found that t is equal to TL is equal to TR, right? And so that is the tension in both sides of this cable, right? So TL and TR are equal to T, and T is 3935 newtons. Okay, so that would be the solution to that problem. And now, let's take a look at a third example here, where we ramp things up just a little bit more. In this case, we have a similar setup here. This is a traffic light of mass 15 kilograms suspended from 2 wires. But here we have 2 angles, so it's not that the traffic light is in the middle of the 2 cables. It's off to one side, giving us 2 different angles, and these are not the same angles that we saw before, right? Before we saw angles that were like up here, right? But in this case, we have angles on the other side, so we have to be careful how we transfer these tensions into their components, which is what we're going to be doing in a moment here. But this is the setup that we want to work with, so let's get started with that. Okay. So first step, as usual, is going to be free body diagram. And we already know that drawing the diagram with these angles in there isn't really going to help us. We want to break up T1 and T2 into their components in the x and y direction, right? So we're going to impose a coordinate system like this. This is going to be our x direction. This will be our y direction. And we're going to want to break things up such that we have a free body diagram that looks like this, right? So horizontally, we're still going to have well, I guess what I did here was I called them T2 and T1 instead of TL and TR. That's fine. So what we're going to have here is we're going to have T2, the x component of T2 pointing in that direction. We're going to have the x component of T1 pointing in this direction. Then we're going to have T1y and T2y both pointing upward in the y direction, and pointing downward in the y direction. We're going to have the force of gravity, mg, right? And so again, what do we need to do? Well, we need to break up our T1 and T2, which are like our TL and TR from the last example, into their vertical and horizontal components. Okay. And so maybe I'll draw a little picture here, and we can do that again. So let's take a look at T1. T1 is kind of a vector that points like this, and we know that we have an angle here of theta 1, right? So what do we want? We want this is T1. We want a T1x and a T1y like that. And from the diagram and our knowledge of trig, we can right away write down that T1x is simply going to be T1 times the cosine of theta 1 right? And T1y is going to be T1 times the sine of theta 1, right? And we can see that right away because the adjacent side to our angle corresponds to T1x, and that's the cos that we want, and T1y links up with our sine, right? And the same idea is going to work for T2. Again, T2 is simply a vector that points like this, so this will be T2. We have this angle in here, which is theta, and we want T2x and T2y like that. So this is going to tell us that T2x is going to be equal to T2 cos theta 2. Careful, this should have a 2 on it. And T2y is going to be T2 sine theta 2. Okay. And so now that we've broken our T1 and T2 up into their vertical and horizontal components, into their components pointing in the x and y directions, we again want to break the problem up into its horizontal and component, or at least we want to look at the horizontal and component and vertical components separately, using Newton's second law. Let's give us a little dashed line here, and let's take a look at horizontally again. Okay, so horizontally, what's going on? Well, Newton's second law tells us that F net, the net force in the x direction, is going to be equal to mass times the acceleration in the x direction. But again, the acceleration in the x direction is 0. There is no acceleration in this problem. The whatever it's called, traffic light, is just hanging there, right? And this is going to be equal to the net forces in that direction. So that's going to be T2x minus T1x, right? And it's T2x positive because it's pointing in the positive x direction, and T1x points in the negative x direction, so it picks up a minus sign. And because the two of those are equal to 0, this is telling us that T2x equals T1x, and we can substitute in what we found, T2 and T1x, to be in terms of sines and cosines of theta 1 and theta 2 here to get the following. So this tells us that T2 cos theta 2 equals T1 cos theta 1, right? And I'm just going to rewrite this one more time because here it's not quite as simple, right? Like last time when we were doing this, this led us to an expression where our T1 and our T2 were being hit by a cos or a sine. I don't remember which one it was, but basically of the same angle. Here we have different angles inside our trig function, so they won't just divide away, right? So we can rewrite this. Let's write T2 equals T1 times cos theta 1 over cos theta 2. Okay, and we'll keep that equation for later. I'm going to call that equation A. Okay, so we have that equation from our horizontal calculation. Let's see what's going on vertically. So we're not yet ready to solve the problem. Obviously, we need to take a look at what's going on vertically. Okay, so vertically, I think I have some notes for the numbers here. Right, okay, so vertically, again, we're going to look at Newton's second law. And what does Newton's second law tell us? Well, it tells us that F net in the y direction is equal to mass times the acceleration in the y direction. And again, the acceleration in the y direction is 0, so this has to be equal to 0. If we look at the net forces, what do we have? Well, in the positive direction, here we can look at our free body diagram. In the positive direction, we have T2y plus T1y. And the negative direction, we have mg, force of gravity pulling downward. Okay, and because this is equal to 0, again, we can rearrange this to give us T2y plus T1y equals mg. And as we've done before, we've built these expressions that we can make a substitution in for T2y and T1y in terms of T2 and T1. So let's do that. So T2y is just T2 sine theta 2 plus T1y, which is T1 sine theta 1 is equal to mg. Okay, so let's keep our eye on the prize here. What are we trying to find? We're trying to find T2 and T1. We want to know the tensions in these cables. That's what the problem is asking us for, right? Find T2 and T1, or T1 and T2, the magnitudes of the tensions in these wires. So we need to solve for T1 and T2. We have T1 and T2 in our equation A, and we have T1 and T2 in what I'm going to call here our equation equation B, let's say. So we have two equations and we have two unknowns. That means that we can solve this system, right? We have two equations and two unknowns, which means it's a well-defined system. We can solve for both of them. What we're going to do is we're going to substitute in the value of T2 into equation B. So we're going to substitute equation A into equation B, clean things up, and from there we'll be able to solve for T1. Let's go through that here. Okay, so we're going to take A in B. So we're taking equation A and substituting it into B. And if we do that, so we're basically replacing this T2 over here with everything in equation A, right? So what do we end up with? We end up with T1 cos theta 1 over cos theta 2 times sine theta 2 plus T1 sine theta 1 equals mg. Okay? And so it might not look super clean at this point, but we're actually at a point here where we can solve for T1, right? T1 is the only unknown that we have in here. We know what theta 1 is, we know what theta 2 is, we know what m is, we know what g is, so T1 is the only unknown, and if we manipulate this algebraically, we can then solve for T1. So let's do that. We're going to factor out a T1. So T1 is factored out. We end up with a cos theta 1 over cos theta 2 sine theta 2 plus sine theta 1 equals mg. And I think we can all see that we can now divide out by a term in the brackets, but I'll rewrite it one final time just so we have it written down here. So T1 is going to be equal to mg all over cos theta 1 over cos theta 2 sine theta 2 plus sine theta 1. And that's basically it. So at this point, we would substitute in numbers. I won't write out the full substitution, but basically you have theta 1 and theta 2 up here. So you would simply substitute in 30 degrees for every theta 1, 45 degrees for every theta 2, take the sines and the cosines as you need to, and then substitute in for m and g, divide mg by this bunch of different trig functions, or the value you get from that. And if you did that, you would find that T1 is equal to 108 newtons. Okay, so that's T1, but we also need T2. Well, what's the simplest way to get to T2? Then we just take this T1 value, T1 into A from up here, right? Substitute T1 back in there along with our theta 1 and theta 2, which we already know. So we get T2 equals T1 cos theta 1 over cos theta 2. And we know what T1, cos theta 1, and cos theta 2 are, so if we make that substitution and put it into our calculators, we end up with a T2 of 132 newtons. And that's the answer to this problem. So all these cable problems will go somewhat similarly. So again, just like the problem where we had the mass on the incline with a skier last video, these are all going to follow similar ideas. So we're going to see these a few more times. Keep the sort of flow of the problem, like the way you would solve this, in mind, because you're going to see them again and again. So you want to be comfortable solving these types of problems. Okay.